Welcome. In this session in linear data analysis, we'll perform PCA, or principal components analysis, on some data that have labels. I generated this data, and I generated it as 300 points and accumulated it in a data matrix A. These were inside 3 ellipses, so 100 points in one ellipse, 100 points inside a second, and 100 points inside a third. I then merged 2 of these ellipses so that they have the same label. The labels here are -1 and +1, and I compute the mean, the scatter matrix, and then perform the principal components analysis on this data. In addition, I'll carry the labels onto the loading vectors, and what this will allow us to do is understand how the loading vectors and the data interact. This is the data. So in this red region, these are all within one ellipse, and these are 100 points. And then in cyan, I have 2 ellipses. One is a large ellipse, and one is a small ellipse. And these together have 200 points. So I have imbalanced data. When I perform principal components analysis, the white X indicates the mean of all of the data, and the large arrow indicates the first loading vector, and the smaller arrow indicates the second loading vector. So we can see that the loading vectors are aligned with the major and minor axes of this original data. When we project the labels onto the axes, this is what we get. So I've slightly offset these axes so that we can see what's happening. And we can see that the red data are going all the way through on this first axis, and that the cyan data are concentrated in one zone, but they're actually also scattered along this first loading axis. Well, what do the data look like on the second loading axis? Well, this second loading axis is curious because for our data set, it looks as though it's doing a better job of distinguishing the labels. So previously, what we've wanted PCA to do is to give us a way to score the data, and we want to find the maximum eigenvectors. Now, what we're interested in doing is starting to do a classification problem, and that begins with what we would like to do is break these data into 2 subsets, partition the data ideally, but break them into 2 subsets. And it looks as though this second loading vector is doing a slightly better job than the first loading vector. So this requires a little more investigation. And here what I've done is I've labeled the mean. So this red X is the mean of the large label -1 data, and then the cyan X, which is a little harder to see, is the mean of the label +1 data. And if I perform PCA on the means of the data, what I get is this magenta axis. So this magenta axis is directed between the 2 means, and it goes through the mean of the overall data set. So what I'd like to do now is I'd like to combine the PCA of all of the data with the PCA of the means of the data and see where that takes us. So what have we got so far? Well, we can color the data labels. In MATLAB, we can just use the gscatter function. And PCA with a scatter matrix, this is finding the first loading vector is a maximum variance. And then if we think about it, here we're working in 2-dimensional data, but it works in n-dimensional data just as well, is that the last loading vector is the minimum variance, and for some data that's a better one to look at. And we really don't know at this point why we should be looking at the maximum versus the minimum loading vector when we have data that have labels associated with them. One observation we can make is that, for better or worse, PCA is treating all of the data uniformly, and it's not taking into account the labels of the data. So a problem that we have now is how can we use this extra information about the labels of the data in doing principal components analysis?